is there some kind of easy way to explain why you wouldn't be able to use gradient descent in a common kind of situation that you encounter, and why you would need to use a Gurobi solver instead?
Yeah. So one of the benefits of using mathematical optimization is it guarantees two things. One is it guarantees that what we call feasibility is that when you set up all of your constraints and you have your decision variables and you have all this sort of stuff and you click go, that you're guaranteed that all of your constraints will be satisfied. And and the number two thing that you're guaranteed is global optimality. And that's something where methods like gradient descent and all these other things.
They can just get stuck in a local minimum.
Perfect. Yeah, yeah,
Yeah.
exactly. Um, so, so having that global optimal solution is is something that is unique to mathematical optimization. It's not a heuristic method, as we call it. Something that is a really good approach, but you may not get the actual optimal solution. With minimizing your cost function, you could probably set up ways to get tweak it, just get a little bit better performance, but by and large things are good enough. When more simpler algorithms to solve those things are good enough for you. You don't want to spend years trying to tweak it so that you get that little bit. But in a lot of business sense, again, you don't want to leave money on the table. And if you can cut like fuel costs, if you're a big company, you can cut fuel costs by 1%. That's huge. That's a couple of the advantages of using uh, you know mathematical optimization. And I would say that the feasibility one that I mentioned is shouldn't be overlooked, because nothing would be worse than like going to like your boss or somebody and be like, all right, here's how you should do this. And then all of a sudden you just run out of resources, you run out of money, or you run out of people, you run out of something, and they look at you and like, wait, I thought you said this was doable. So those are like two of the main reasons why mathematical optimization is super powerful, is because it guarantees those things. And if you do violate the constraints, or if those constraints need to be violated, then the first thing you're going to see is, hey, from Gurobi or any other solvers, hey, your model is infeasible. And you're like, okay, well, maybe it could just be that the recipe that I set for this problem just doesn't work, or maybe you had a coding error or something was wrong. But that's a possible outcome, and then you sort of dive back in and figure it out. But once you do get an answer, then those two things are true, that's feasible and globally optimal. And the global optimal thing I want to emphasize is really important, because you can go into a meeting with some people about, okay, here's how I want to solve this problem. And then you can in words describe the constraints. In words, you can describe the objective, you can describe the decisions that you're making. And if you get a thumbs up from anybody like, yep, that's exactly what our problem is, and you take this modeling approach and you get the solution that you have the confidence to say there does not exist a better solution. There may be some other solutions that are just as good, and we can dive into those. But you don't have there does not exist anything that is better, and that's a real powerful thing to be able to say, and have
Totally.
that confidence in when it comes to making decisions.
That's really cool, man. The In my head, I've been kind of imagining, as you've been talking, I've been thinking about with like a really simple regression model where um, you have just one input variable into the model. So this is described by y equals mx plus b, like the
Mhm.
simplest line equation. Um, if you plot a if you plot a some data points, and you're trying to like solve with that very simple linear equation y equals mx plus b, instead of using stochastic gradient descent, you can confirm without beyond the shadow of a doubt, you can use a mathematical approach very straightforwardly, and it's something that we've been doing in statistics for a century. You
Mhm.
can you can try out, all the possibilities and confirm for yourself for sure in that very simple problem, y equals mx plus b. that you have absolutely the best possible line of fit to those data points, and you're going to get exactly the same result every single time you do it because it's just math. It's not
Yeah,
there's no
exactly. Yeah.
there's no stochasticity, there's no sampling. You're just always going to converge on an exact right answer for how that line should fit the data.